So questions, either in chat or raise hand to unmute. Redox reactions. All right. Yeah, okay. So do you have is it like from a day you're looking at? Because I can pull that up as well and screen share it. If you want to look at like a specific problem, or I can just make up a problem. That's no issue. Let me just look up like a redox problem example. I can work it out. October 4th. Sure, we can look at those too. Well, I don't think redox problems are that hard once you get, you know, what's going on. It's really the tricky thing about redox problems, I think, is on learning all the rules, like all the things you need to do. So let me pull up October 4th here. All right. Okay, so be like question 2. So we can do question 2A, and I'll write that down, and then I will Google one to see if I can find like a little more difficult one, see if I can find someone with nuance. But so redox. So first thing, what we need to remember for redox, we just have to remember what it is. And it's a reaction in which electrons move from one compound to another. And there's an acronym we use for redox reactions called oil rig. Where oxidation is loss of electrons. Reduction is gain of electrons. All right, so if we look, so I'm just going to do 4A, lithium plus oxygen goes to lithium oxide. Li2, 2 of those. And then we need 4 of those. All right, so the first thing we need to do is assign oxidation states to everything. And these are where our rules come into play. And hopefully after going through quantum mechanics, some of these rules will be easier because we've been talking about a lot this semester, like what charges should molecules have? And it's the same thing in redox reactions as it is in ionic reactions. But first off, if a molecule is by itself and there's no charge, then the oxidation state of that molecule is 0. Or, whoops, did not mean to do that. Or if the molecule is bound to itself, it's 0. Right. So the reactants, lithium and oxygen, both have an oxidation number of 0. Lithium oxide, okay, oxygen in a compound that's not itself, so oxygen with any other molecule, the majority of the time it's going to be -2. Lithium is a group 1 metal. Group 1 metals are always +1. And so if we look, lithium went from 0 to +1, right? And remember, electrons, this is something else you kind of need to know to really understand these problems. Electrons are negatively charged, right? So if I lose electrons, I become more positive. So going from 0 to +1 means that's a loss of an electron. So lithium was oxidized, which is called the reducing agent. Remember that terminology as well. If something is oxidized, it is the reducing agent. Oxygen went from 0 to -2. So oxygen became more negative. That's reduced, which makes it the oxidizing agent. So that's the problem from that we did in class. And I'm just looking at some example problems online. And the sample problems online are just as simple, but I'll do one really quick here. So we have AS, 2AS plus 3Cl2 goes to 2AsCl3. So AS by itself is 0. Chlorine bound to itself, it's 0. Chlorine in a molecule, it's a halogen, so it's always -1. Here we have 3 chlorines plus AS, and in total, since we don't have a charge, in total, their oxidation numbers have to equal to 0. Chlorine is -1. We have 3 of them, so it's -1 plus a -1 plus a -1, which is overall, all the chlorines are giving -3. So AS, to balance that, must be +3. So AS went from 0 to +3. That was oxidized. Cl went from 0 to -1. That was reduced. Yeah, if a compound has a charge, that's used instead of 0. So for example, here's another example problem that's online. Let me just get my window straight here. So we have Cr plus SN4 plus goes to Cr3 plus SN2 plus. Here, it's really simple because the charges are telling you what the oxidation numbers are. So Cr has an oxidation number of 1. That's plus means +1. Sn has an oxidation number of 4. Cr on this part has an oxidation number of 3. Sn has an oxidation number of 2. So if a molecule is charged, one, it has the oxidation number of that charge. If it's a compound, like for example, zinc, OH4 2-, and you were asked, okay, give the oxidation number of everything. So for zinc, oxygen, and hydrogen. Overall, the oxidation number of zinc plus your oxygens plus your hydrogens must equal the charge, which is -2. Hydrogen in a compound is always +1. Oxygen in a compound is always -2. And we have 4 copies of this. So it's like -2, -2, -2, -2, +1, +1, +1, +1. So overall, these 4 OHs, if you add up everything, so -2, -4, -6, -8 from the oxygens, and then I'm going to add the hydrogen. So -8 + 1 is 7, 6, 5, 4. This is -4 overall. So zinc must be +2 to balance that out to get an overall charge of -2. So the actual oxidation numbers of each element is zinc is +2, oxygen's -2, hydrogen's +1. Don't forget, you got to distribute when you have these subscripts down here. This means you have 4 copies of OH. what else do people want to know? Again, if you want to talk, type it, just feel free to raise your hand. Otherwise, just put it in the chat and I'll answer any and all questions. Thermodynamics. What about thermodynamics? Test 3. Okay. So we have thermodynamics and we have enthalpy. So let me go to, oops. So I might have to open up test 3 here. So give me 1 second when I do that. It would be number 7 and 10. So number 7, so hopefully I have the right version of the test up because I'm at my home computer. But number 7, I have a system does 87 joules of work on the surroundings and loses 52 joules of heat to the surroundings. What's delta E? And 10 is 1.5 moles of sucrose is combusted in a bomb calorimeter, yada, yada, yada. Okay. Let me do those, and then I will talk about enthalpy. But let's do 7 and 10 from test 3. And so let me get my whiteboard back out. Okay. So now we're doing tests. I hate when my pen does that. Test 3, question 7 to begin with. All right. So get my windows straightened out so I can write and still see what I'm doing. There we go. So system does 87 joules of work on surroundings and loses 52 joules of heat. What is delta E? All right. So for this, we have to remember how to calculate delta E. And one way we can, and remember, delta means change. So one formula to calculate change of energy is that the change of energy is equal to the heat plus the work of a system, right? So I always find it helpful to, like, I don't know, draw a little picture where I say, this is my system, and this is my surroundings. So if I'm doing work on the surroundings, work is leaving me. So if work is leaving me 87 joules, that means my change in work of the system is negative because it's leaving. So work is minus 87. And I'm losing 52 joules of heat as well. So work, heat. So if I'm losing 52 joules, that's also negative. So the change in energy for this is minus 52 minus 87, which should be negative 139, if I did that right in my head, joules. So that's the change in energy. So yeah, for that, if you're giving heat plus work, that's what you need to do. Let me unmute you. Yeah. Whoops, sorry. think I just muted you again.
Okay. Okay. So it would be negative 52 minus 87. So it doesn't have to do anything with the plus sign. Is that correct?
Well,
so like if I plugged it into the calculator, it would be negative 52 minus 87.
Yeah, I mean, you could do
Okay.
plus negative 87, but it can't, like, that plus sign's not doing anything.
Okay.
Yep.
Okay. I just wanted to make sure that so I don't do it wrong when I put it in my calculator.
No, that's exactly what you do. Yep.
Okay. Thank you.
Yep. All right, now let me do 10. And then 10 is, so I have come on, pen. I have 1.5 moles of sucrose. And this is a bomb calorimeter. So in a bomb, my temp was at 27 C, is now at 29 C. What is delta E reaction for the combustion of sucrose in kilojoules per mole if heat capacity of the bomb is 4.50 kilojoules Celsius? All right, so before I just jump into the math, let me take a second so we can understand like what actually is going on with this problem. So I have a cylinder, and this cylinder is my bomb. And inside this cylinder, like I have like a little chamber, and inside that chamber is my sucrose. So I have 1.5 moles of sucrose in that chamber. And I explode the sucrose, explosion. That's why it's called a bomb, explode. And so that releases heat. Heat is being released. Oh, it's doing that again. Heat is being released. So all of the heat from blowing up the sucrose is being absorbed by the bomb. So we have a thermometer that is watching this reaction for us. And that's how we know how much energy is giving off by blowing up sucrose. We can measure the temperature. And I want to know, if I blow up 1 mole of sucrose, basically, how much heat, or how much energy is released. So the first thing I need to ask myself is, okay, I just did an experiment. My temperature went from 27 to 29 C. How much heat is required to do that? How much heat was released by that? And that's where heat capacity comes in. Remember, heat capacity is how much energy you need to put in to raise the temperature of your object. So this 4.5 kilojoules per Celsius means that I need to put in 4.5 kilojoules of energy to raise the temperature of my bomb by 1 degree centigrade. All right. So here I raised it 2 degrees centigrade, 27 to 29. So the amount of energy that my bomb absorbed is 4.50 kilojoules per Celsius multiplied by 2 Celsius. Celsius cancels out. The amount of energy that my bomb absorbed was 9 kilojoules. However, we're not quite done yet because I want kilojoules per mole. That is, I don't want to know how much 1.5 moles of sucrose, gave off. I want like a number I can look back to. I want to know for every 1 mole of sucrose, how much energy is released. And so what you can do is you just take how much energy was released that you just calculated and divide it by how many moles of sucrose you had. So I had 1.5 moles of sucrose. And so now my units are kilojoules divided by moles. And so I just divide those two numbers. And let me get out Excel here so I can do that calculation. 6. So the answer here is the combustion of sucrose, it's 6 kilojoules for every mole of sucrose. Again, the logic is I blew up 1.5 moles of sucrose, measured the temperature of that, knew how much energy was released, and then I just divided by how many moles of sucrose I started with to get this unit of kilojoules per mole. So questions about that? Or Sophia, what were you, so you said enthalpy. Do you have a problem in mind, or can you expand on that idea? Or if anyone has more questions about the bomb, I'll be happy to answer those as well. Or anything at all, really. If you have, for those of you just joining us, what we're doing here is if you have questions, put them in the chat. If you want to just talk about them, feel free to raise your hand. I can unmute you. All right, just the concept, sure. And I'll get to you in a second, Claudia. So enthalpy. So enthalpy is basically another word for heat. And there's a couple different ways which we designate that. Usually it's delta H. So anytime you see delta H, that means enthalpy, right? So we talked about different ways of calculating delta H this semester. You'll also see it as Q. For the energy calculation we just talked about, heat and we called it Q. That's not quite enthalpy, but it's very similar. So some terminology to go with enthalpy is if heat goes into your system, and this is my surroundings, because anything that's not my system is my surroundings. If heat goes in, that's called an endothermic reaction. Endo and in, so heat is going in. So if heat's going in, Q is a positive value for my system. And now that heat had to come from somewhere though. So it came from my surroundings. So it's minus Q. So let's say that my system absorbed 10 kilojoules of heat. So the amount of heat for my system is a positive 10 kilojoules. For my surroundings, it's a negative 10 kilojoules. They're equal but opposite. And that's the same thing with work. While if heat leaves my system, so out, that's called exothermic. Exo means like exiting. So here, Q is negative. I guess, let me get a different color. So if I'm leaving, Q is negative for my system, while Q is positive for my surroundings. So equal but opposite. Does that make sense? Or were you looking for like something else? That's what I think when it comes to enthalpy. Okay, and then Claudia, I think I saw you with your hand raised, so go ahead. And then we have Kimberly after that. Okay.
Test on the photon light energy.
Test 3, photon light energy.
Yes. I don't have the test with me yet, so I'm
Sure.
but there was one that it was like you're changing from 1.5 to 2, and then there was one that was like a whole different equation formula.
So I have one that's a heat lamp produces 20 watts of power at a wavelength of 7 times 10 to minus 6. How many photons are emitted per second? Or which of the following transitions represent the absorption of the smallest frequency? I think I have to ask you to unmute again if you muted yourself again.
The first one you said.
Okay, heat lamp, sure.
Yeah.
So let me go over that one. Okay. And so we have heat lamp. I'll get the right pen out. There's my box of a lamp. So 20 watts of power. And this is test 3. Question, was it 14? Yeah, question 14. Could you also, I'm gonna get to Kimberly, and then I'll get to question number 9 on exam 3. Right, so question 14, so 20 watts of power, where 1 watt equals 1 joule per second. And the wavelength equals 7.7 times 10 to the minus 6. Meters. So the question is, how many photons are emitted per second? All right, and so to do this, one thing, so let's think of the different things we need for this. First, we have to understand that a photon is a particle of light, and photons have energy. And the energy of a photon is measured in joules, right? And we also have an equation to go from wavelengths to joules, and I'm going to look up the constant for that. Planck's constant. No. So the energy of a photon equals Planck's constant times the speed of light divided by my wavelength. Planck's constant, as I just had that, is 6.626. Then the units are joules per second. The speed of light is 3.0 times 10 to the 8th meters per second. And wavelength is in meters. Sorry, I got my units wrong. It's joules times second. 6.626 times 10 to the minus 34. There it is. And so our meters are 7 times 10 to the minus 6. So the first thing we are asking ourselves is, based on this wavelength of light, what is the energy of one photon? And that is this equation. Energy of one photon equals Planck's constant multiplied by the speed of light divided by the wavelength of your light. So if I do that, so equals 6.626 times 10 to the minus 34 multiplied by the speed of light, 3.0 times 10 to the 8th, divided by the wavelength of my light, 7 times 10 to the minus 6. The energy of one photon is 2.84 times 10 to the minus 20th joules. So really, really, really tiny. Now, I have a light source that is pumping out 20 joules per second worth of energy. So 20 watts, where 1 watt is 1 joules per second. I want to know, if one photon is that small, how many photons are in 20 watts? And we can use our train track for that, where I have, 2.8184 times 10 to the minus 20 joules. So one photon is 2.84 times 10 to the minus 20 joules, right? So how do I want to do this? So I'm actually going to redo my train track, sorry. One photon is 2.84 times 10 to the minus 20 joules. And I have a light source that is giving off 20 joules for every 1 second. So really, I take how strong my light is, which is 20, divided by the energy of one photon. So I'm doing 20 divided by 2.84 times 10 to the minus 20th, which should be a big number. So for every second, I'm pumping off 7.04 times 10 to the 20th photons. So a lot of photons are coming off at that light at one given time. So just to recap that, one, you need to figure out the energy of one photon. So that's this equation, E equals Planck's constant, speed of light multiplied by speed of light divided by the wavelength of light. Then you take your light source, which is 20 joules, divided by the energy of one photon to figure out how many total photons you have. Make sense a little bit? And let me get Kimberly, since her hand has been raised for a bit, and then I'll do number 9 on exam 3. So
Hi, Dr. Andrews.
Hey.
Question was on test 3. The two questions that had to do with the graphs. I kind of had a little understanding on question 3, but question 1, I didn't understand that one.
All right. I think for this one, it'll probably be easier if I just share the test then. So let me switch my screens. There we go. All right. So these questions, like for the graphs, I'm guessing these are going to be like questions the ACS will sneak in there, because it's really testing, do you really understand this concept? If you do, we can ask you it in a way that maybe you haven't seen yet. But if you understand the concept, you can figure it out. All right. Which of these gases have the lowest density at STP? All right. So if you have, first off, what's STP conditions? So we're dealing with a gas here. So PV equals nRT. So anytime we deal with a gas, we want to talk about the ideal gas law. All right. And at STP, you're at standard temperature and pressure. So pressure is at 1 atmosphere, temperature is at 0 Celsius or 273 Kelvin, right? And so if we're at these conditions and all of these gases are in the same volume, that means all of these gases, A, B, C, and D, have to have the same value of N, right? Because if P, V, T, and R is a constant, if these are the same for gases, then N is the same for all of those gases. All right. So once we know that, we have to think about what's density. Density for a gas. It's basically molar mass divided by molar volume. And we already just said molar volume's the same. So really, the only difference between A, B, C, and D then, based on all of this, is their molar mass. So what moves faster, light things or heavy things? Well, light things do. And so your gas, A, is moving the fastest on average. So what you're really looking at is you're going to the middle of the peak and just saying, which of these gases is moving the fastest? And just take the average, really. Or I guess it's not the average, it's the median. But A, on average, their molecules are traveling faster. And so they have to have the lowest density, meaning they're the lightest. Oh, actually, let me keep that up for a second in case you're still writing, or those of you chose to write. And then for C, or 3, that's kind of a trick question. Which of these gases have the highest average kinetic energy? Gases at the same temperature under the same conditions, kinetic energy is the same. So the answer here is they have the same kinetic energy. So as long as you're at the same temperature, no matter how heavy you are as a gas, you always have the same average kinetic energy. And then let's go question 9, since we're still on exam 3 here. Oh, Kimberly, did you still have something you wanted to say? Because I still see your hands up.
Oh, yeah. No, sorry. I didn't.
Oh, no, so just didn't lower your hand. That's fine. Okay, I'll do that. So let's go to question 9. All right, what is the change in internal energy for a system that gives off 20 kilojoules of heat and shrinks from 10 to 5 liters if the external pressure is 2 atmospheres? All right, so this is a somewhat similar question to one we already did, where the change of energy is equal to heat plus work. All right, and so first off, we are giving off heat. So if we're giving off 20 kilojoules of heat, that must mean Q is negative, so minus 20. Now we have to figure out work. Here, we're doing pressure volume work. And so our equation is whenever you see a volume change under a pressure, work equals minus P delta V, dV. So you'll either see it written as dV or triangle V. Anytime you see like delta like this, that's always final minus initial. So my change in volume is I was at my final is at 5. And initially I was at 10. My volume was -5 liters. I shrunk 5 liters. And my pressure, so when doing this calculation to figure out work, you need both pressure and volume. I'm at 2 atmospheres of pressure. So I multiply those two together. And remember, this is a negative. So if volume's negative, pressure is positive. All right, I'll say that again. Since there's a negative sign in front of my equation, if your change in volume is a negative, your overall work will be a positive. So the amount of work that I do is 10 liters times atmosphere. It's a weird unit. However, you see my heat's in kilojoules. So if you want to add two numbers, they have to be the same unit. So I need to convert from liters atmosphere to joules. And that should be all the way up here. Yep. And so from our sheet at the top, 1 liter atmosphere is 101.325 joules, right? So now that I have that, let me go back to the actual problem. All right. So I have 10 liters atmosphere that I calculated. For every 1 liter atmosphere, that's 101.325 joules. There is 1,000 joules in 1 kilojoule. Make sure you remember how to do your metric conversions. Liters atmosphere cancel out, joules cancel out. So I'm left in a unit of kilojoules now is what I want. So this is 10 times 101.325 divided by 1,000, which is, doing that calculation, I got 1.013 kilojoules. So I'm going to rewrite my equation up here. It's getting a little messy. So heat was -20. Work was positive 1.013. So my change in energy for this system is -20 plus 101.3. My delta E is -18.99 kilojoules. So that's how you do that problem. Do I know if there will be questions on defining laws, other definitions? So I haven't looked at the exam, and even if I did, I could not tell you what or what isn't on it, because that would bias you, as in like kind of fishing out what's on. I would be prepared to know what, you know, some of the laws, what that meant. What does Charles' law mean? What does Boyle's law mean? If I had to guess, I don't think they're going to give you straight definitions, but they might ask you a question where that's in the text of the question, where it's like, according to Boyle's law, blah, 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 blah. And you have to know what Boyle's law is to solve it. That would be my hunch. So for work, either pressure is negative. Well, pressure can't be negative. The equation is, right, work equals negative pressure delta volume. So pressure is always going to be a positive number. So whether work is positive or negative depends on the change in volume. If your volume shrinks, that means work is positive. If your volume expands, if this is a positive number, that means overall this would be a negative number, work is negative. That negative sign in front of the P, that's just so the work is the correct sign. Formula sheet, I would highly doubt the ACS will give you a formula sheet. They're going to give you a periodic table. They're going to give you constants. Yeah, I would be. I'm trying to think of because I looked at an old exam back in the summer, and yeah, I don't think there's equations at all, unfortunately. Claudia, I saw your hand go up, then it went down. So all clear on that, on whatever issue you have? Okay, now it's up again. Yeah, what's up?
I was just gonna ask, because you have some of your old tests up, those have formula sheets, right? So I can go back and write down like some of the equations and things like that, so I can study them separately.
Yeah, so my old exams definitely have formula sheets on them. So yeah, it would probably be helpful to look at those formula sheets and figure out what do the symbols mean. Okay, once I know that, what is this equation used for? That's a very good way to get that down. And I will say, like I don't like these, like the problem I just did, I don't necessarily have all these equations memorized, like work equals minus P delta V. The way I remember that is all through units, because I know if you go on the very top, and this will be something they'll give you. They'll give you like constants and some conversion factors. So I knew that there's a conversion exists that goes between liters, atmospheres, and joules, right? And so I knew if I multiplied my pressure in atmospheres and my volume in liters, I could convert that to joules, which gives me energy. So if you're going through a problem and you don't remember the formula, the best thing you can do to give yourself a chance is to look at the units, right? And I've said this a couple of times, but the units always will help you find the answer. If you go back to the bomb problem we did like at the very beginning, where I want my answer in kilojoules per mole. Here I give you something in a unit of mole. Here I give you something that's in kilojoules divided by Celsius. Here I give you something in Celsius, right? So if you can recognize that you have to get kilojoules by itself by multiplying by some Celsius, and then taking your kilojoules and dividing it by some moles to get your final answer of kilojoules per mole, you're going to give yourself a better shot at getting the answer right. Granted, it takes a little more because you have to know to do minus initial here to get a positive number of 2, but still, you're going to give yourself a fighting chance to, once you start paying attention to those units. What else do we have? I saw a raise of the hand and then go away again. All right. A bunch. So we have the last 2 problems on the same test. And then I see 2 hands raised. So let me do the, since we're on this test, let me do those and then I'll get to the raised hands. All right. So first off, write an equation for the formation of NH2COH. All right, so a formation equation is basically you take compounds in their stable state, so like N2, H2, O2, and C, and you combine them to make NH2COH. So this is nitrogen plus hydrogen plus oxygen plus carbon makes NH2COH. In a formation equation, you can use fractions on your reactants. So my product has 1 nitrogen. Here I have 2 nitrogen, so I can just do 1/2 N2. This is like the only time you can use fractions. One of the only times is when doing formations. On the right-hand side, I have 3 hydrogens. Here I have 2, so I need to multiply that by 3/2. Oxygen, 1 on the right, 2 on the left, 1/2. Carbon, 1 on the right, 1 on the left, that's fine. Next, we have what is the enthalpy of reaction. That comes from these delta H numbers. And it's always going to be products minus reactants. So you add up everything on the product side minus everything on the reactant side. So FeCl2 is minus 399 plus 4.4 plus NH420, 82.05. And I'm going to subtract that from my reactants, Fe0 minus 272 plus, now I have a 2 here, so I have to multiply my next number by 2. Then NH4Cl is negative 314.55. And so do that really quick here. 399.4 plus 82.05 minus negative 272 plus times negative 314.55. Let me just double check my math here. Negative 901 plus 901. Okay, so I got delta H is 583.75 kilojoules. Right, so let's go to the raised hands now. So Kimberly, what's up?
It was this one. I had a question on test 3. Could you go question 16?
Yeah. Which of the following represents the smallest absorption of the smallest frequency photon? And then we have a question about precipitation reactions. All right. So this is, so 16 is something I actually mentioned on Wednesday. So when we talk about energy levels, the first thing to remember is that the higher energy you go, the energy levels start to shrink. They start to get closer and closer to each other until eventually they're like right on top of each other. Right. Also, when you go up in energy, you are absorbing light. When you go down in energy, you are emitting light or emitting energy. Okay, so first off, let's just see which ones are actually absorbing. B isn't, that's emission. So we cross that off. C's emission. Right. So we already canceled 2 of our options off just by understanding what's absorbing and what's emission. All right. Now we want the smallest frequency. All right. So let's remember what frequency is. Frequency is how many times a wave hits a certain point per unit of like seconds. So if I'm like standing right here and I have like 2 different waves, I have one wave that looks like this. And so if I'm watching it comes towards me, it's going to hit me a lot of times per second. So this is high frequency. And that also means high energy. Versus another wave that may look like this, right? That wave is not going to hit me so many times in the face compared to my black wave. So this is low frequency, low energy. So if I'm talking about the smallest frequency, that would be a very short jump. So that would be like to 5 to 6. Very tiny jump there. And so precipitation reactions, and also question 4 on test 4. Let me do precipitation reactions. Get off my whiteboard. Let me just find a random precipitation reaction. Oh yeah, we need our rules for that. That's right. Yes.
The one on the slides are okay. The 30 ml sample of 0.2.
What date is that from?
Oh, sorry. A lot of slides in this one. October 1st.
October 1st. All right, let me pull that up. And I'll share that then. All right, so first thing we need to know is our precipitation rules. So basically, your group 1 metals always soluble: lithium, sodium, potassium, and ammonium. NO3 and acetate always soluble. Halogens always soluble unless with silver, mercury, or lead. Then SO4, except with like a bunch of these. OH minus, like never soluble. S2 minus, never soluble, unless it's with these 6. So these 6 molecules, if you see them in a compound: lithium, sodium, potassium, ammonia, nitrate, or acetate, that's what that's called, always soluble. So let's take a look at this. So lithium iodide plus barium sulfate. And the question is, do we have a reaction and is it soluble? So what you do to figure this out is all you do is you switch your metal ions around. So I have lithium and barium. This will make barium iodide plus lithium sulfide. And then you ask yourself, and this should be lithium 2 sulfide, barium iodide 2. Are these soluble, right? So your sulfur is insoluble unless it's with lithium. So lithium is soluble. And iodine is also soluble. There's no exceptions for, well, there are exceptions, but Ba is not one of them. So this is also soluble. So what happened here is that I mixed two things together. Both of these things were soluble, so actually no reaction happened because I didn't form a solid. So let's go down to our other examples. So we have sodium hydroxide plus iron chloride. So again, we're just going to switch around the metals. So sodium chloride plus iron OH3. And the reason why I know it's 3, again, let's review this. Halogens, -1. We have 3 of those. So -1, -1, -1, all together make -3. This is a neutral compound, so iron must be +3. So first off, sodium chloride. Chlorine is soluble unless it's with silver, mercury, or lead. Sodium's not any of those, so it's soluble. OH is generally insoluble unless it's with lithium, sodium, potassium, ammonia, nitrate, or acetate. So this is insoluble. Iron is not one of our 6 molecules. So our reaction is NaClAq, aqueous means dissolved in water or soluble, plus iron hydroxide solid. And then we go to B. Let's do B as well. Switch the metals. We'll make KBr plus lithium hydroxide. Potassium is always soluble no matter what, aqueous. Lithium is always soluble no matter what, aqueous. So those, remember, those 6 at the top always soluble. So no reaction. Nothing happened here. Unless you make a solid, you'll never have a reaction. Question 4 on test 4. Let me see here. Okay. So again, question 4 on exam 4 is, again, has to do with energy levels. Which would emit light with the highest energy? So again, do our energy levels. The higher you go up, the closer they become. And again, if I go up, that's absorption. If I go down, that's emission. So since I'm emitting light, I have to go down. So B, it can't be B because I'm going up. Can't be C because I'm going up. Right. So if I'm emitting light with the highest energy, that means I make a, I went down a lot. So the question is, what's a bigger gap? Going from 6 to 5 or 4 to 2? And it's 4 to 2. That's a giant gap compared to 6 to 5. Can I go over number 2 on question 4? Yeah. All right. So question 2, which one doesn't exist? All right, so let's remember the rules. N can be equal to 1 to infinity. 1, 2, 3, 4, 5, all the way to infinity. L can equal to 0 all the way to n minus 1. M's of L is equal to minus L to plus L, including 0. So minus L, 0 to plus L. This is range. M's of S only ever has two values. Plus 1/2, minus 1/2. So if we look at A, n is 2. So if n is 2, I can have two possible L values. My L can be either 0 or it can be 1. Remember, so the s and p orbitals. So if you look on your periodic table, you go to the second row, you'll notice there's no d orbital there. You only have s and p orbitals. All right. And so once we have that, so this is fine. L is 0 is fine. N of 2, that's fine because it follows this rule. So if L is 0 and we have M's of L minus 1. Well, if L is 0, M's of L can range from minus 0 to 0 to plus 0, right? Minus L to L. Well, if L is 0, that's only one value. That's 0. So if L is 0, M's of L has to be 0. It can't be any other number. So that's what makes that false. If L was 1 here in A, if L was 1, M's of L could be minus 1, 0, or plus 1. So if I just did something like that, then this becomes a true orbital. That's fine, as long as L is equal to 1. But as long as L is equal to 0, M's of L can only be 0. Can I do 15? Isoelectronic means they have the same electron configuration, right? So let's do, so C is the right answer, right? So nitrogen has the electron configuration of helium, 1s2, 2p3. Well, if I go to N3 minus, I get 3 electrons. So N3 minus is helium, or not 1s2, 2s2, 2s2, 2p6, or neon. O2 minus has the same electron configuration. F minus has the same electron configuration. Na plus has the same electronic configuration. Mg2 plus as well. So that's what isoelectronic means. Every molecule in that list has the same electron configuration. What else? So let me do test 2 question. What was it? Sorry, I did not realize I was muted there and I was talking to myself. So test 2 question 11 part B and polar non-polar. Question 11. Okay. One sec. I think maybe the copy I have on my computer is different because I don't have a part B. So let me look that up really quick. Sent. Okay, that should be the right test. Yep. Okay. Got it. Let me share that. All right. So for the following reaction, I combine 25 milliliters of H3PO4 with 35 milliliters of NaOH. So I'm going to do part A because I can't do part B without doing part A. What's the reaction? All right. This is an acid-base reaction. Hydrogen, acid. So if you have hydrogens out in front like this, that's telling you an acid. Compound with OH is a base. Remember an acid-base reaction, acid plus base equals salt plus water. So H3PO4 plus NaOH makes water plus a salt. Your salt's always going to be metal and non-metal. So plus NaPO4. Hydrogen has a +1 charge, oxidation number. Sodium has a +1. Therefore, if I needed 3 hydrogens to go with my PO4, I must need 3 sodiums to go with my PO4. So again, using stuff we've learned in different sections, you can see it just comes back over and over and over again. These ideas of what is the charge of my molecule in a reaction? Sodium's always +1, hydrogen's always +1. So now I have to balance this reaction out. So it's 3 sodiums on the left, 1 on the right. So put a 3 there. That now makes it 6 hydrogens to 2. So put a 3 there. That should be a balanced reaction, no? And so what is molarity of NaOH? So remember, molarity equals big M equals moles divided by liters. So I know how many, and this is for NaOH. So I need 2 things. I need to know how many moles of NaOH I have, and I need to know how many liters of NaOH I have to solve this. All right, so I know how many liters because it says I have 35 milliliters of NaOH. So 35 milliliters for every 1,000 milliliters, that's 1 liter, 0.035 liters. So that's how many liters of NaOH I have, right? Now I need to figure out how many moles. Well, I don't have that in my reaction, but I have molarity of H3PO4. I have liters of H3PO4. Those combined can give me moles of H3PO4. And using stoichiometry, I can figure out how many moles of H3PO4 I have. So my solution is I have 2 moles of H3PO4 for every 1 liter of H3PO4. Remember, that's what big M stands for. How many moles you have for 1 liter. But I don't have 1 liter of H3PO4. I only have 25 milliliters, which is 0.025 liters. So the question is, in 25 milliliters, how many moles of H3PO4 is that? So liters cancel out. So it's 2 times 0.025. Which is 0.05. So that means I have 0.05 moles of H3PO4. Now that you're in a unit of moles, remember, if you're in moles, you can use stoichiometry to go to any other compound in a balanced chemical reaction. So remember, I'm trying to get moles of NaOH. So for every 1 mole of H3PO4 I have, that takes 3 moles of NaOH. So 0.05 multiplied by 3 is 0.015. So in this reaction, I have 0.15 moles of NaOH. So now I know how many liters of NaOH I have. I know how many moles I have. I can now calculate my molarity by dividing the two. So 0.015 moles NaOH divided by 0.035 liters NaOH. So we'll do that. So my molarity of NaOH is 4.29. Yeah, so these acid-base problems are quite involved because they're using a lot of different things. One, you have to know how to balance reactions. Then you have to know stoichiometry. Then you have to know molarity. So let me go over polar and non-polar now, and then question 2 on exam 9. We'll do that next. And well, we also have Kimberly with her hand raised. So let me go polarity, then Kimberly, then question 9. And that was the order that I saw all those in. So let me pull up the PowerPoint that we started on Wednesday. And again, polarity was something that those of you in lab, which I think should be pretty much all of you, we did extensively on the week of Thanksgiving. All right, but let me share this. All right, so draw a molecule and determine whether each molecule is polar or non-polar. So let's do A and B here. So sulfur chloride. So sulfur has 6 valence electrons. Chlorine has 7. So you're going to make 2 covalent bonds. And once you do that, you have to know the geometry, right? So you have sulfur with 2 lone pairs and 2 bonding groups. So 4 total electron groups. 2 of those are bonding groups. 2 of those are lone pairs. The distance between the bonds is it's the same distance as water. And it's around 109. It's not quite, I don't think, but it's around there. All right, so that's the first thing. The first thing is to figure out the geometry. The next thing is to look at our electrostatic numbers and determine, is this a polar bond or not? And so I need to get up that sheet because I don't have those numbers memorized. So let me pull that up really quick. And by the way, those of you who are in lab, the best way to get this information is the molecular modeling lab because it's all in one place. So the number for chlorine is 3. So chlorine has a score of 3. Sulfur has an electronegativity score of 2.5. So you subtract those two numbers and you find that the difference between those numbers are 0.5. So when chlorine and sulfur bond, they have a difference of 0.5. And if it's, I think, is basically 0.5 or greater, that's a polar bond. Right, so now we draw arrows. And the way we draw arrows, since it's a polar bond, the arrowhead will go towards the molecule that is more negative, right? And you're asking yourself, do these arrows cancel out or do they not cancel out? So if I have an arrow going to the bottom left and an arrow going to the bottom right, so I have this. And I'm not sure if you all are great at thinking about vectors, but if I have something going to the corner like this, what that means is I have 2 different motions of force. I have one motion is going straight down. And then on the arrow going to the bottom left, it's going to the left. On the arrow going to the bottom right, it's going to the right. And so you're asking, do these vectors cancel out? Well, the left and right one do. But the bottom ones don't. They actually add together. So since arrows that go like this don't necessarily cancel out, this is a polar molecule. Let's look at this for SCl4 though. For SCl4, what happens is that these 1, 2. So 2 of my, so one of my lone pair is now gone. And I have a lone pair in 4 chlorine. So that's what SCl4 looks like. And then we go to our geometry sheet that's also in Blackboard, so in the final exam folder of Blackboard. And we got to look up this geometry. So let me share that screen for you. Where was it? There it is. All right. So SCl4 had 5 groups because it looked like this. And so it has 4 bonding and 1 lone pair, which is sawhorse or seahorse. And so what that means is that you have a chlorine going in this direction. You have a chlorine going in this direction. So they cancel out because they are doing the opposite direction. But then you have a chlorine going down here and a chlorine going over here. Again, these don't cancel out. So SCl4 is polar. And that's what you really need to do for polar and nonpolar. 1, determine if there's polar bonds. Once you figure out if there are polar bonds, you have to see, do they cancel out? So just one more example, CO2, right? CO2 looks like this. I don't know the scores, but I know they're polar bonds, where you have an arrow going towards the oxygen and the other arrow going towards the other oxygen. However, since it's linear, the arrows are going the opposite ways. So CO2 has polar bonds, but it's non-polar because the arrows I make cancel out. Right, so then we had Kimberly, and then I'm going to test 2. So I need Kimberly, yes.
So my question, well, I just wanted to see if you thought if they would give us like electronegativity scores or what do you think we need to result to like the arrows and all that?
You would probably get electronegativity scores. I would be surprised if they asked you a question on that without providing you that information.
Okay, and for like naming acids
Mhm.
and ionic compounds,
Mhm.
could you go like into like the differences between acids, the naming of acids compared to like ionic compounds?
Sure. Do you happen to know what date that was again?
It was in 3.5, section 3.5. That's
Okay. Let me dig.
section 2.
Molarity. Oxidation. Because it would be really cool. I don't want to rewrite everything because I know the PowerPoint just has these nice little tables that tell you if this, then this. So that must have been at the end of this one. Let me find it. So it must have been test 2. Calorimetry. No. Solutions. Ionic. I can't find the slide, but I'll just do it off the top of my head, I guess. All right. So first off, ionic compounds. Yeah.
I found it. It was September 10.
Okay. So I was close. I clicked everything but that. September 10th. Oh, it's forever ago. All right. So there's 2 things we have to remember for ionic compounds. Well, first off, what is an ionic compound? That's a metal and a non-metal. So remember on your periodic table, we have like this black ladder. It's always some kind of black indent they put there, more or less. But everything here is a non-metal. Everything to the left's metal, right? So if you combine these, one of these each, metal and non-metal, you get ionic compound. All right. Now, metals, group 1, always have a +1 charge. Group 2 has a +2. SC has a +3. Aluminum, zinc, silver, +1, +2, +3. No matter what, the metals that are highlighted here always have that charge. So if you have metals with that charge, for example, NaCl, the way you name them is rather simple. you give the name of the metal, sodium. And then the name of the non-metal plus I, sodium chloride. Or this would be sodium oxide. Or I don't know, potassium sulfide. However, that's the simplest case. However, what if you use a metal? Actually, let's go to periodic table. What if you use a metal that doesn't have a known charge? So all your transition metals, basically. How do you name that? This is where Roman numerals come in. So iron. Oh, what is the name of that? Well, we know oxygen is a -2 charge. We know that from me saying it a bunch of times, but also through oxidation rules. We know that from our Lewis structures now that oxygen wants to be -2 in a reaction. We know that a bunch of different ways. But the question is, what is the charge on iron then? Well, if it's a 1-to-1 ratio like this, remember, metal plus non-metal has to equal a 0 charge. So if oxygen is -2, iron's +2. This is called iron to oxide. How about, I don't know, VF3, right? Well, F is -1, so V must be +3 to interact with 3 fluorine. So this is vanadium 3 fluoride. You name the metal plus whatever charge it is plus non-metal. And the only caveat to this is when you're doing polyatomic ions, you have to give them their special names. The naming scheme of the metal's the same, iron 2 versus sodium. But if you're giving like sodium acetate, that's how you would name it, sodium acetate. Oops. Or this. This is iron 3 acetate. So the metal is determining whether you use Roman numerals or not. For acids, well, first, hydrated compounds, that's when you use hemi, mono, di, tri, tetra, penta for the number of waters. And if it's all nonmetals, you just use prefixes. So, or sorry, yeah, all nonmetals, right? So as I have here, nitrogen and 3 iodides, nitrogen triiodide. There's nothing tricky about that, but this is non-metals only. There's a lot of times where I see, what's the name of this? And I'll get monosodium monochloride. And that's not correct. You only use these prefixes for compounds that are only non-metals. Acids, okay. If it's a binary acid that is only 2 things, then it's easy to name. So HCl, you always say hydro, then the name of the nonmetal, chlor, and you add ic acid, chloric acid. H2S would be hydro sulfuric acid, sulfuric acid. HF, and it's always going to be H something, hydrofluoric acid. If it's a compound that's not a binary acid, then it gets a little silly. But basically, if your polyatomic acid ended in an 8, so sulfate, it becomes ic acid. So H2SO4 is a combination of hydrogen plus sulfate. So we call that sulfuric acid. HNO3 is hydrogen plus nitrate. So that's nitric acid. However, if your oxy ion ends in an ose, or sorry, ends in an ite rather, ends in an ite, it becomes ose. So here we have hydrogen plus NO2. NO2 is nitrate. So that's why it's nitrose. Note, these do not get hydro in front. That is wrong. This is not hydrosulfuric acid. This is just sulfuric acid. This is just nitrose acid. Hydrogen plus sulfite with sulfurose. So really for this special naming scheme, you're looking for multiple oxygens. That's when you have to do this ic or ose if you see multiple oxygens appear. So yeah, the naming of, I think these acids are the trickiest, but yeah, keep in mind, hydrogen in front means it's an acid. Multiple oxygens, it gets the ic or ose naming scheme. Otherwise, it's a binary acid. So it's just hydro, name of the acid, name of the nonmetal, ic acid. All right, and then let me go to the question that's question 9 on exam 2. Let me go back to exam 2. What is the products for the following reaction? All right. So this is a another solubility question. So what you do is you switch the metals. You ask, do you make something that's soluble? So we have potassium and aluminum. So you make potassium chloride because potassium's +1, chlorine's -1. So it's 1-to-1 ratio. Potassium with anything is always soluble, so that's aqueous. And you make aluminum carboxylic or carboxide. Okay, you have to figure out the ratio of this. So we have to go back to our compounds. So potassium's always +1. But I have 2 of those, which means CO3 must be -2 to make that a neutral compound. Cl is -1 always because it's a halogen. I have 3 of those, so overall that's -3. That means aluminum's +3. So I have aluminum that's +3, CO3 that's -2. So to balance this, you just move your coefficients across. So this is Al2, CO3, 3 of those. And if you go to your solubility rules, you'll CO3 is generally insoluble and aluminum's not a solid, or sorry, a reaction, so that should be a solid. So yeah, that's a solubility question. All right, I probably have time for maybe one more question. Do you think we'll have questions regarding the elements in the f orbitals? No, I don't think so. Those are so weird that you might have questions as in what is their electron configuration? Possibly that, but like that would be the only thing. I'd be surprised if you're asked like questions about f orbitals. And the only thing that's different about the f orbitals when you're doing electron configuration is that, you know how we did d -1? So whatever row you're in, So like if you're in the third or fourth row, that means you're in the third d orbital because it's n minus 1. The f orbital is n minus 2. So that's supposed to be a 1 up there. So for example, the electron configuration of element 57, lanthanum, would be, start with Xeon, then we are in the 1, 2, 3, 4, 5, 6 row. So 6s2, 4f1. Because you see in the periodic table how it kind of just pulls out at the lanthanum at 57. So that means, oh, we're in the f orbitals now. I don't think you're going to get questions on that, but it's not impossible. All right. And yes, see your hand is raised again. What's up?
So just a quick question on question 9 that you went over. So would that be K2Cl2 or would that just
Nope, just KCl.
KCl?
Because it's 1-to-1 ratio, because K is +1, Cl is -1. So you don't need any twos. It's not balanced yet. I didn't balance it. Let me balance it really quick. So you have 2 Ks on the left, 1 on the right. So you need a 2 right there. But you have 3 Cls. So you're going to need at least a 3 for my chlorines. So my chlorines are balanced. And this is going to be a real pain in the butt to balance. So let me actually, I'm going to need my table because I can't do this one in my head. AlCl. Reactant, product. So we start off with 2, we made 1. So I'm going to get rid of that 3. I'm going to start over. CO, we had 1. We have 3 now. Al, we have 1 on the left, 2 on the right. And then chlorine, we actually have 6. I didn't see that with the arrow. And 6, and then 1. All right, so balance this. So I need at least 3 COs. So that's 3. That make that 6. I need, oh, I do have 2 aluminums. Yeah, that 2 is there. And so 6. So that's the balance reaction. 3, 2, 6, 1. Any other like quickish questions? Because I'm probably going to call it in 5 minutes because I have biochem coming up at 3. And I'm going to need at least a couple minutes in between to let the video save and rest my voice. But I can answer like any quick questions. And if you have more in-depth questions, what you can do is you can email me. I will also be available Monday morning. There are other chemistry professors available Monday as well. I'll put up their schedules. So if you want to talk to them, like if you're studying over the weekend and still have a question, we can definitely have another discussion on Monday. But any quick last minute questions here? Yeah.
When is it that we take away the electrons from the s orbital before the d orbital? Is that what I'm talking about?
I think you're talking about the s orbital before the d, because we didn't really talk about f
Yes.
orbital because it's so odd. Basically, let's say that you have titanium. The electron configuration of titanium is argon, 4s2, 3d2. I want to know what is the electron configuration of titanium 2+. You always take away from the 4s, from the s shell before the d shell. So this would be 3d2. It's with the d orbitals that you do that. You take away from the s, then you can take away from the d. So Ti plus 1 would be argon 4s1 3d2. Ti plus 3. So these are all valence electrons. So the number of valence electrons in titanium are 4. And here it's 2. Here it's 3. Titanium 3 plus 3d1. It's just 1. Yes.
Okay. So going off of what Claudia said, so what about if the electron? No, if we were talking about valence electrons, like she put in the chat,
Mhm,
if the element is inside the D block
mhm.
and you're counting valence electrons, would you count the valence electrons plus the s orbital?
Yep. So let's take a look at this. So iron is argon 4s2 1 2 3 4 5 6 3d6. That has 8 valence electrons. However, once you get past the d orbital, so let's look at selenium. Selenium's element number 34. That is argon 4s2 3d10 1 2 3 4 4p6. Once the d orbital's full, we don't, not 4p6, sorry, 4p4. We don't count that anymore, right? So full, it's not valence. So the total number of valence electrons in selenium is 6. Oh, did you have something else to add?
Yes, okay, so I just want to clarify. So
Uh-huh.
if the element is inside the D block, you count the valence electrons to get to that specific
You count
element.
you count the S and the D together if it's in
Yeah.
the D block. Yep.
Okay, and then if it's outside of the D block, you do not count it.
You ignore it. You only focus on the S and the P. Yep.
Okay, okay, thank you.
Yep. All right, so it's 2:50, so I think I'm gonna take a 10-minute break before I start my next class. So thank you all for coming. Yeah, got good. Not the 30 people I saw raising their hands on Wednesday, but still, fair amount. So thank you for showing up. I will post this online in case in case you came in late and you wanted to see what we went over earlier. Like I said, if you have questions still, the test is until Monday. So if you're looking over the weekend, you want to meet, let me know. Monday morning, like I'll be available in my office if you want to stop by then. If you want to have a Zoom meeting, email me. We'll get on Zoom for there. Otherwise, good luck. Sleep well, eat well. Yes. Thank you all for coming. And good luck. Take care, everybody. I'll tell them I said, everybody, you're welcome.